The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presenter is Muzai Feng. He's a PhD student also from University of Kansas. He got his bachelor's structural material science and engineering from Southeast University, China, and his master's is in civil engineering from UK.
Thank you all for coming and good afternoon. My name is Muzai with University of Kansas. Today I want to introduce a test method that we have developed in our lab that is largely based on ASTM C157, but allows us to capture the early age deformation of concrete specimens. Now, before we start, I want to take a minute and thank all the sponsors who provided funding to this project, including the Strategic Development Council at ACI Foundation. The presentation will start with an introduction, which I will briefly talk about concrete shrinkage and cracking. And following that, I will talk about the existing method that aims to capture the early age deformation of concrete specimens. And after that, I will talk about ASTM C157 and our modifications, followed by some case studies featuring the behavior of concrete mixtures containing shrinkage-compensating admixtures. And finally, I will wrap up with a summary. There are two types of shrinkage we are mostly concerned here. Plastic shrinkage and drying shrinkage. Plastic shrinkage takes place when concrete is still in plastic state, and it is caused by the rapid loss of mixing water, usually caused by the excessive evaporation rate associated with high wind speed, high temperature, or low relative humidity in the environment. Drying shrinkage, on the other hand, is caused by the loss of moisture, long-term loss of moisture in hardened concrete. Now, in both cases, due to the loss of moisture, the total volume of concrete is reduced, and we'll have shrinkage. Now, why do we care about shrinkage? As Amir has explained, imagine a slab of concrete. It can be either a slab on grade or bridge deck. For whichever reason, if we have some shrinkage in the concrete, the adjacent structures, such as piers in bridge deck or reinforcing steel, or even adjacent concrete, will try to force the shrinking concrete in its original shape. And this will develop a tensile stress in concrete. And as we know, concrete is strong in compression, but it's very weak in tension. And at any point of time, if the tensile stress caused by shrinkage, restrained shrinkage exceeds the tensile strength, we'll have cracking. And it's not hard to imagine that the deformation of concrete is more important in early ages because concrete is weak at early ages, and the shrinkage, or rather the tensile stress needed to crack a concrete is much lower compared to when the concrete is better cured. Now, cracking in concrete structures, as James has explained, accelerates the deterioration of concrete structures. And while they may not always reflect a structural issue, they certainly will make users feel insecure, and sometimes they may be an aesthetic issue. And finally, the cracking in concrete structures is usually very expensive to repair. Existing test method that evaluates the early age deformation includes several. The most widely used is ASTM C157, in which a cement paste or mortar is cast in a corrugated plastic tube. The tube is then sealed with two plugs, then placed on a supporting device shown in the picture. One end of the tube will be fixed, and the other end will be connected to a displacement sensor, which allows continuous measurement of the deformation. This test method has been proven really consistent and reliable, and has been adopted by many research projects. But there are several drawbacks of it. The first of which is it cannot be used on concrete which contains coarse aggregate. And also, this test test setup cannot be used to measure drying shrinkage because the specimen is always sealed in the tube. And finally, the test setup can be expensive, especially when you try to measure multiple specimens out of multiple mixtures. The number of the setup needed quickly goes up. Another test method is shown in the figure here. There are several variations of this setup, but the working principles will be the same. Generally, the side of the molds will be removed after initial set, and two displacement sensors are connected to the specimen. For the consistency of the measurement, the specimen is also usually left in the mold, and the sensors need to be somewhat connected to the mold. And the drawback for this test method is that the friction between the concrete specimen and the bottom of the mold can be significant, and it can be a restraint that limits the deformation. And also, for drying shrinkage measurements, this setup can be inefficient because the specimen needs to stay in the mold. Now, with those background information, I want to talk about ASTM C157. This is a test method that measures the long-term deformation of concrete specimens, usually drying shrinkage. The specimens are demolded 1 day after casting. Initial length is measured. After that, the specimens are cured in a saturated lime water. In our project, we use 14 days, but you can use 28 days also. The length of the specimens are measured after curing and as well as regularly during the drying period. The expansion during the curing and drying shrinkage during the drying period are calculated using the initial length measured by the end of the 1 day, but at the time of demolding. Now, if we have an axis for time, we have casting at 0 hours, we have demolding at 24 hours, and we have end of curing at 14 days. The initial length in ASTM C157 is measured at demolding. But if you think about it, if there's any point of time that we should be concerned of, it's the final set time. Once the concrete has started to hold its shape, any expansion in it will cause a compressive stress, and any shrinkage will cause a tensile stress. And the standard test method essentially missed the deformation that's taking place from the final set to demolding. With that in mind, we set out and tried how early could we demold specimens. And after trial and error, we found that for our mixtures, which is 0.45 watt cement ratio with 23.4 paste volume, we could consistently demold specimens at 5.5 hours and get good readings. Now, since we demold the specimen early, we can take 3 to 4 readings during the first day, and we also decide to take length measurements daily during the curing period. Since this test method is based on ASTM C157, it's very easy to operate and it's very economic. If you're running C157 already in your lab, you don't need to add any additional equipment. And finally, this test method allows us to continuously monitor the deformation during the curing period and drying period. Now I want to show some of our test results. The first question we had was, what do we do with specimens in the first day? Now, the specimen was removed from the mold 5.5 hours after cast, and we want to keep the specimen as close as the standard test situation as possible. So we tried two methods. For some specimens, we wrapped them with a plastic sheet and made sure that the exchange of moisture was limited as good as we could. And for other specimens, we put them in saturated lime tank. Now, here's the results obtained from the specimens in both storage methods. We have shrinkage on vertical axis in the unit of microstrain, and we have time after casting in the unit of days on horizontal axis. We can see that the specimens that were wrapped by plastic sheets, represented by the red line here, were almost identical with the specimens that were placed in saturated lime water. Now, since keeping the specimens in lime water was much easier to operate, we proceeded with this method. So our complete method is demold specimens 5.5 hours after cast, measure initial length, keep them in saturated lime tank, measure length change regularly after that. The second question we had was, how comparable are our results with ASTM C157? Because we have hundreds of mixtures that were tested using the standard test. We want to know if we can compare the results directly, or if not, what kind of conversion do we need. Now here we can see that the test results obtained using the standard test agreed really well with the modified test method on control mixture. Now this is also true for most of the ordinary mixtures, and that is why the standard test method has been a reliable test for decades, and it is still a valid test for ordinary mixtures. However, in the recent years, we have seen an increased popularity of shrinkage-compensating admixture. This is a type of solid powdered admixture, usually contains calcium oxide or magnesium oxide. When they're mixed with cementitious material, they will react with mixing water and form calcium hydroxide or magnesium hydroxide, causing an expansion. Now, coupled with restraint, this expansion will induce a compressive stress in concrete, which will counteract the tensile stress caused by shrinkage. And I also want to note here that shrinkage-compensating admixture should be distinguished from shrinkage-reducing admixture. Shrinkage-reducing admixture also usually abbreviated as SRA, works by reducing the surface tension of a porous solution. So when concrete loses moisture, the driving force for shrinkage is lowered. So at a given period of time, our observed shrinkage is reduced. On the other hand, SCA, or shrinkage-compensating admixture, works by inducing an early age expansion and usually does not affect shrinkage. Now, when we first tested SCA in our lab, we found that using ASTM C157, we only observed 50 more macrostrains of expansion by the end of 14-day curing period compared to the control mixture. However, later on, we adopted this modified method, and here we can see that by demolding early, we observed 300 more macrostrains of expansion on the mixtures containing SCA. When we put the results for SCA mixture using both methods together, we can see by demolding 5.5 hours instead of 24 hours, we captured almost 200 more macrostrain of expansion. Now, since we also take length measurement daily during the curing period, here we can also compare the behavior of different types of shrinkage-compensating admixture. All the previous slides are shown are the results from a calcium oxide-based SCA. Here I added the results for a magnesium oxide-based SCA. We can see that magnesium oxide-based SCA induced an expansion that is more steady over the entire curing period, represented by the blue dots. Now this feature can be useful in massive concrete because you can design the dosage of the SCA, or you can choose different types of SCA such that the expansion can counteract the shrinkage that is caused by the cooling down of the massive concrete. And finally, I want to talk about the behavior of SCA and SRA mixes. Here we can see the mixtures containing an SRA induced much less expansion compared to the mixtures containing SCA. But after the 14-day curing period, and the drying shrinkage rate is much reduced compared to the calcium oxide-based SCA. And finally, I want to note that the magnesium oxide-based SCA that was commercially available to us had a part of shrinkage-reducing admixture in it. So here we can see, although it did not expand as much when compared to the calcium oxide-based SCA, the drying shrinkage is much reduced. And to wrap it up, I introduced the modified ASTM C157 test method that allows us to capture early age deformation of concrete specimens. It is very easy to operate, and it is very economic. And also it captures early age deformation as well as drying shrinkage. And the results are compatible with the results obtained using the standard test method. And as a case study, we explored the behavior of shrinkage-compensating admixture. There are two types of them, and the magnesium oxide-based SCA had a more steady expansion, whereas the expansion of calcium oxide-based SCA was more rapid. And we also distinguished between the behavior of mixtures containing SRA and SCA. With that, I'm open to questions.
Thanks a lot. That's good work. I'm just a little curious. How many specimens did you demold and lose the end pins?
When we first started, we started by demolding 4.5 hours,
Yeah.
and we lost a lot. So later on, after trial and error, we moved to 5.5 hours. And if after several trials, get some experience, we can consistently get all the specimens.
So after 5.5, 6 hours, you were consistently able to demold without losing pins.
Yes, and as a safety measure, we always cast 4 specimens, where we only need 3.
Just in case one fails.
Yes,
right?
we always have one more.
You should put that in the method, right? Yeah.
With that interesting effect of the calcium hydroxide, if we are doing conventional 157 tests, and if we are curing our specimens in a lime water tank, will we therefore be grossly underestimating the shrinkage that we would actually see in the field?
That is correct.
So we need to stop lime curing if we're doing shrinkage tests, right?
Yeah, especially when you're doing shrinkage-compensating admixture.
Well, but even if you're not, if the source of the calcium oxide is the lime water curing tank, and you've demonstrated that the lime water, whether the source is internal or external, is going to have an impact, seems to me that our standard method is way wrong. I may have misunderstood your talk, but it looks like there's a very beneficial impact of the introduction of calcium and magnesium oxide, that helps.
Yes, yes.
Right, that gives us an expansion rather than a contraction.
Yes, yes.
Okay, but in many routine lab operations, we take our curing specimens and we put them down in a lime water tank, which seems that we're then going to get some of that expansion that you identified. And if that's true, then we are grossly underestimating the real shrinkage that we're going to get if we're not in a lime environment. Okay. Thank you. Thank you very much.
I'm sorry.
Thank you.
I think the statement that you're making is very valid. My limited understanding of these types of expansive admixtures, however, is that they are based on calcium oxide, free lime, and the conversion of free lime to calcium hydroxide is what causes expansion. So when you put the sample in a lime water bath where the form of lime is hydrated lime, so that expansion has already happened, that there shouldn't be a problem.
Thank you.
I don't think the lime water made a difference because we didn't have the slides there, but we actually cast 12 specimens of each mix, placed 3 in the curing room, which just has, mist, 3 in the lime water, and 3 covered with a plastic sheet. And we didn't see any substantial difference. So I don't think the lime water is causing any, based on what we saw.